In this video, we will be focusing on thermodynamics, which is chapter 16 from your book. So previously, hopefully you guys have studied or learned a little bit about thermodynamics, some basics about thermodynamics in Chem 101 course. So we'll be building on those concepts, try to get few more details regarding how thermodynamics works for chemical processes. So by definition, what is thermodynamics? It's the study that allows us to understand how the energy changes, what is the flow of energy, and how is the work associated with the chemical process. And why is this important? Because it kind of gives us the information if a reaction is going to occur or not, if a chemical process will happen by itself, or do we have to supply energy from outside for this reaction to occur. So it kind of gives us the predictability if a reaction will happen by itself or do we have to supply energy for it to happen. For instance, like kinetics, we studied how we can predict or control the speed of a reaction. Similarly, thermodynamics helps us to control if a reaction would actually happen by itself or without any interference from outside at a particular condition, under particular conditions. Okay. So just to go over some brief review of the concepts that you guys know from beforehand, I'm going to keep this really quick. So you guys learned before the first law of thermodynamics, which essentially tells you that the energy of the universe is constant. You cannot create energy, we cannot destroy energy, right? Energy can only be changing in different forms. So for instance, as heat energy can change into kinetic energy, potential energy, mechanical energy. There are different forms of energy, but you can never destroy or never create energy. So energy of the universe is constant, which means change in energy. So if you guys remember this symbol right here, delta, it's called delta, the small triangle. That is the difference in energy, right? So delta stands for difference. So energy difference of the universe is always zero. Why? Because we cannot create energy, we cannot destroy energy. So that essentially there's no change in the energy. Total energy of the universe stays constant. So the change in energy is going to be zero. And if you guys remember the concept of having a system and the surroundings, so if this is the universe in type total, if this is the universe and this is the system that we are interested in, everything surrounding that system is called the surroundings, right? So energy of the universe, which is this whole thing, is going to be equal to change in energy of the system and change in energy of the surroundings. And since delta E of universe is zero, that means that whatever is the change in energy of the system, the change in energy of the surroundings is going to be exactly same with just an opposite sign, right? So hopefully you guys remember this concept from beforehand. Another concept that you guys have seen before is enthalpy. What is enthalpy? Enthalpy is just the change in the energy or the heat of a reaction. So during a chemical process, either energy is absorbed or energy is released. So you guys should be familiar with this concept. What is an exothermic process? What is an endothermic? Exothermic processes are the processes which release heat or they produce heat, meaning exit comes from exo, right? So delta H in that case is a negative symbol or a negative sign. Whenever delta H is negative, that means it's an exothermic process. Whenever delta H is positive, that means it's an endothermic process where energy is absorbed during a chemical reaction, right? So these concepts you guys are hopefully familiar with. If not, I gave you guys a brief review about it right now. If you want more details, you can go back and look into your previous topic from Chem 101, but this is essentially majorly what you need from that topic. Okay, so the new concept that we are going to build up now is the concept of entropy and something about spontaneity, Gibbs free energy, and all those concepts. Okay, what's important here is I told you previously that why is thermodynamics important? It allows us to predict if a reaction is going to occur spontaneously or not, or is it going to happen by itself under these conditions, or do we have to supply some energy from outside? How can we decide that? That's based on two considerations. One of them is enthalpy, which you guys are familiar with. The second one is entropy, and we'll talk about more uh, about entropy in detail in the next few slides. Okay, so first let's begin with the term spontaneity. So you heard me use this term right now. If a reaction will happen spontaneously or not, right? So what do I mean by spontaneous? A spontaneous reaction or a spontaneous change is something that would occur without an input of energy from outside, which means we, at a certain condition, we do not have to supply any energy from outside. This reaction or this process is going to happen on its own. What do I mean by that? For instance, if we have some ice cubes right now, and the temperature outside, let's say, is 80 degrees Fahrenheit, and if you place some ice cubes outside in this heat, what is going to happen? They are going to melt, right? So this solid ice is going to melt to produce liquid water. This process of melting of ice cubes on a warm day is a spontaneous process. We are not giving it any energy. We are not changing anything. At this particular condition, it is going to melt, right? So that is a spontaneous process. For instance, a lump of sugar, if you add it to a hot cup of water or a cup of coffee, it's going to melt, right? Sorry, not melt, it's going to dissolve, right? So that essentially means this process is a spontaneous process. It's going to happen on its own. Similarly, for instance, right here, iron, if we expose iron to air, after a while, it's a slow process, but after a while, it is going to rust, right? If it's exposed to oxygen and water, eventually it will produce rust like this. So this is a spontaneous process. We don't have to stop, there's no way for us to stop it unless we supply or remove some form of energy, right? In the simplest form, the example would be, let's say if there is a water body and water would always flow downhill, right? It's never going to flow uphill. So water that flows downhill is a spontaneous process, okay? On the other hand, what's opposite of that? It's called a non-spontaneous change or a non-spontaneous process. What is non-spontaneous? Something that will not happen on its own. It will only occur if the surroundings continuously supply energy to the system. So essentially, we have to continuously supply some form of energy to the system for this particular reaction to occur. For instance, if we have a pile of bricks lying around, it's not just going to make a brick wall by itself, right? Water is never going to go uphill on normal conditions. Unless you supply it some energy, that's the only way you're going to be able to take water uphill, right? So that those kind of processes are non-spontaneous process. Example, decomposition of water by electrolysis. So water just by itself, if I take some water and I place it in a glass or a container, it's not just going to suddenly convert into hydrogen gas and oxygen gas, right? This decomposition of water only happens by electrolysis. So you have to supply electrical energy or some form of energy to dissociate water into its components, right? So that kind of process, which continuously requires a supply of energy, are non-spontaneous changes. For instance, right here, if I have these two bulbs connected to each other by this valve and I have some gas in one of these valves and I open this valve, what is going to happen? All these gas molecules are going to distribute in both these bulbs, right? This process is a spontaneous process, right? On the other hand, if I talk about the reverse process, that is going to be a non-spontaneous process. So if I have gas in both the bulbs, if I want to collect the gas into just one of these bulbs, that is not going to happen by itself. We will have to forcibly supply some form of energy or force these gas molecules to go into just one of these bulbs. So the reverse of this is going to be a non-spontaneous process. So what this means, that if a change is spontaneous in one direction, it will always be non-spontaneous in the reverse direction. So essentially, if this is happening spontaneously, the reverse of that has to be a non-spontaneous process. So a particular chemical reaction will only be spontaneous in one direction. Okay, the processes have a natural tendency to occur in one direction at a given set of conditions. If I change the conditions, the reverse in that case will, if unless I change the condition, the reverse is not going to be spontaneous. So if this is spontaneous, the reverse has to be non-spontaneous under the same conditions, right? Now, a lot of times people think, if I ask you to predict, is a reaction going to be spontaneous or not? A lot of times people think that it has to do something only with energy, change in heat, right? So for instance, if I talk about melting of ice at higher temperatures, what kind of process that is? That is an endothermic process, because melting of ice requires heat to be absorbed, right? So it's an endothermic process. Evaporation of water at higher temperature, same thing. Water evaporates spontaneously. So this is a spontaneous process. It's an endothermic process. Dissolving of the salt, sugar, everything in water, that again is an endothermic process. Okay, and at the same time, it's also spontaneous. So that sometimes people confuse that if a reaction is spontaneous, it's endothermic. That is not true. Let me show you some examples where the processes are exothermic, but they're still spontaneous. For instance, if I take some water and I put it in very low temperatures, under 0 degrees Celsius, it's going to freeze, right? So under that condition, what's happening? It's a spontaneous process. It's going to happen on its own. What would happen to energy? In form of energy, if we talk about, it's an exothermic process. It's going to release energy. Freezing of water releases energy, right? So it's an exothermic process, but at the same time, it is spontaneous, right? So at that particular condition, it is going to happen by itself. Combustion reactions. For instance, if we are burning a candle, right? Or if I burn some magnesium, combustion essentially means burning compounds, right? Their reaction with oxygen. So burning of wood. If I light some wood on fire, it's going to happen spontaneously. And what kind of process is that? It's an exothermic process. Those processes release heat. So an exothermic process, but it is still spontaneous. Okay. So what I'm trying to tell you here is that spontaneity has nothing to do with the energy of reaction, or just solely it does not depend on energy of reaction. You cannot say if a reaction is endothermic, it's going to be spontaneous. Similarly, you cannot say that if a reaction is exothermic, that is going to be spontaneous. Yes, sign of delta H matters, but along with heat change, there's another factor that determines if a reaction is going to be spontaneous or not. And that term is entropy. That particular factor that allows us to determine if a reaction is spontaneous or not is entropy. So whenever we talk about if we want to predict, is a reaction going to be spontaneous or not? How can we predict that? We have to look at two factors. One of them is delta H. Okay. The second one is entropy. Entropy is given by the symbol S. So there are two factors that you have to consider before you can predict is a reaction going to be spontaneous or not. All right. So now let's come and talk about what is entropy. By definition, the easiest definition for entropy is it's the measure of randomness or disorderness of a system. Disorderness, as the word tells you, how disordered the system is. That's exactly what it means. Higher the disorderness of the system, higher is the entropy of the system. Okay, or disorderness essentially just means, for instance, if I have a very clean room, right? Everything is in order, everything is in place. And then on the other hand, I have a room which is completely unorganized. Everything is cluttered. Everything is disordered. So a cluttered room will have higher degree of disorderness, meaning it has higher entropy. That's exactly what it means. Okay. If we talk about on the molecular scale, the model essentially defines entropy in terms of microstate. Entropy of a system is related to number of microstates that are possible for a system. What is a microstate? A microstate is essentially a specific configuration of all the locations and energies of the atoms or molecules that make up a system. So in simple terms, what is a microstate? A microstate is the possibility or the configuration of the location of an atom and the energy of the atom. So if I have a jar filled up with a gas, what locations can an atom occupy? Okay, how many energy levels can that occupy? Those are called as the microstate of that particular system. Okay, so molecularly, if you think about, if I have a system right here, if this is the atom, it can occupy a location right here, have this much energy, a location right here, location right here. It's probable to move around, right? We know there's Brownian motion. Atoms are always moving around. They are not steady. So if they're moving around, they can have multiple locations, right? Meaning they can have multiple possible microstates associated with them. Higher the number of microstates, higher is the entropy. Okay, so in other terms, we can also say the higher is the disorderness. So if an atom is right here, at some point it's going to be here, 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 here. It's just moving around, which means the system is very disordered. This atom is completely disordered. It has very random locations. So higher the degree of randomness, higher is the entropy. So essentially microstate is same as the disorderness of the system. Okay, in easier definition, it's essentially just telling you the location and the energy of atoms. So there's another, how do you relate microstate? So microstate right here is W to entropy. S equals K ln W. This W is the microstate, and K here is the Boltzmann constant, which is right here. Given the value of Boltzmann constant, it's a constant term. Now your book would give you a lot of details about entropy and microstates. It would give you a lot of probability. It goes into a lot of details about probability, possible locations, possible microstates. I do not want you guys to be focusing on that. So only stuff that I'm going to be talking about in this video is what I want you guys to be focused on. Okay, I would ask you to predict the entropy change for a system, but it has nothing to do with microstate. So we are just going to skip everything about microstate, all the further details about microstate that are given in your book. Only thing you should know is what is a microstate, how is it defined, and how is it related to entropy, right? Okay, moving on. So let's try and see how we can predict, how entropy can help us predict the disorderness, or how can we predict the amount of disorderness for a system. So like I said, entropy is measure of disorderness. Higher the disorderness, higher is the entropy. So if I take this particular example right here, what I showed you before, there are two bulbs, there is some gas in one of the bulbs, and there's a valve connecting those. So if I open this valve up, I get into this state, right? So if you think about these two states, which state would you say has more disorderness or more randomness? So in this case, these molecules are very close to each other. They are moving around, but they are only in this particular space. They can only move around in this tiny little space. Now that I've opened up this valve, they have a lot more space to move around, right? Their location can be a lot more. They can be located here. At the same time, I can have a molecule located in this block as well. So now what have I done to the disorderness of the system? I have increased the disorderness of the system. Meaning, what did I do to entropy? I increased the entropy of the system. So higher is the disorderness of a system, higher would be the entropy. Higher is the orderness of a system, so more ordered the system in, lower would be the entropy. Okay, now what is the other thing that you should remember about entropy? Like other factors in thermodynamics, entropy is also a state function. So what does state function mean? Just a reminder, a state function is something that does not depend on the path taken. It only depends on the initial and the final state of your particular atoms, molecules, whatever we are interested in. Okay. So this does not depend on the path, it only depends on the initial and the final values of entropy. So only formula that I want you to remember for entropy is essentially this. If we are interested in figuring out what is the change in entropy, meaning delta S, delta again stands for change, so change in entropy would be equal to final entropy of the system minus the initial entropy of the system. So the difference in the two entropies of the system. Again, it only depends on the final and the initial state. It does not depend how it went between the entropy. It could go from here, 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 which path it took, it doesn't matter. It could take whatever direction as long as there's a final state and there's an initial state. Only what matters is what is the final and what is the initial state. All right. Okay. So delta S essentially is change in entropy, which is equal to final entropy of the system minus the initial entropy. So if the final entropy of the system is higher, our value of delta S is going to be a positive number. It will be greater than 0. So most of the times the kind of question you would see is in this chapter is to predict if the entropy of the system is going to be a positive number or a negative number. So is the entropy going to increase or is it going to decrease? And how can you predict that? Let's look at different factors that help us predict the disorderness of the system. And again, only thing you have to think here is what is happening to disorderness. Is it increasing or is it decreasing? Okay. For instance, one very important factor is physical state. Okay, so physical state essentially is it can be something can be solid, liquid, or vapor, meaning gas. So if I talk about entropy of the system here, in case of solids, you can see molecules or atoms are always arranged in a very ordered system, right? They have a crystalline structure, they are very ordered in comparison to liquid. Liquid molecules are more far apart, they are more there's random location that they can occupy. They're always moving around, is that correct? Which means liquids have more disorderness in comparison to solid. Similarly, if I talk about gases, if you guys remember, gases, molecules are even farther apart from each other. They are moving much faster, right? And they can occupy much more randomness, much more locations. So this on vapor or gaseous state is going to be more disordered in comparison to liquid. So as we go from solid, liquid to gas, we are increasing the entropy of the system. Okay. Same thing, let's say if I have a solute, if I take a tablespoon of salt, I have it as a solute, tablespoon of salt in the solvent, and then it is not soluble. Okay, solute is right here, solvent molecules are right here. This system is going to look like this. But when I dissolve this salt, let's say I have a soluble salt, I dissolve this salt, it creates a solution. What happened to the disorderness of the system? Right now, everything looks very ordered. But once it is in solution, everything is very disordered. So what did we do to the system? We increase the disorderness of the system, meaning we increase the entropy of the system. Other way to increase the entropy or change the entropy of the system is by temperature. So as you guys know from previous thermodynamics experience, temperature is directly proportional to kinetic energy of the system, right? Higher the temperature, higher would be the kinetic energy of the molecules. As we increase the temperature, molecules have more energy, they start moving around, they start jumping around, right? So at a higher temperature, the molecules will start moving around much more vigorously. They're going to move around, they're going to collide with each other, they'll have more disorderness in the system, right? So as the temperature increases, we increase the disorderness of the system and we increase the entropy of the system. Okay. Next thing, if let's say I have this much space, a container, right? I add a certain number of atoms in here. There is an entropy of the system, right? Now, if I add more particles into the system, what is going to happen? These particles are going to collide with each other, right? More particles meaning more collision, more moving around. Their location is going to be more non-specific. There's probability that this particular atom could be colliding with each other and then moving around a lot more. So that would increase the disorderness of the system again. So adding more number of particles would also increase the disorderness, meaning it would increase the entropy of the system. And the last example is volume. For instance, like similar example what we saw before, I have this particular container where all these molecules are arranged in a particular fashion in smaller space, right? Now, if I suddenly remove this barrier, they would have a lot more space to move around. So volume would increase, right? So atoms are going to move around more randomly. There would be more disorderness created because now I have more volume. Kind of similar idea when something goes from liquid to gas. If there's more volume, more space, they're going to move around, right? Even more, meaning this system is going to be much more disordered. So I increase the disorderness of the system by doing this, by increasing the volume, meaning I increase the entropy of the system, right? So some chemical examples that you can see right here. For instance, we have some bromine, which is liquid, changing to gas. So if something was liquid, it's going to be more contained in the container, right? Molecules are going to be more organized in some little space. But as it converts into gas, molecules or atoms are going to have a lot more energy. They're going to move around much more. They're going to collide with each other much more. The likelihood of, again, the microstates, if you think about, is going to increase, because their location, energy, both probability of having them different locations and their energy is also going to increase. So that means if I'm going from liquid state to gas state, for bromine, entropy in this case is going to be positive. So you can predict that delta S in this case is going to be greater than 0. Similarly, you can see right here, if we are talking about iodine solid changing to gas, whenever solid is going to change into gas, it's definitely going to increase the disorderness of the system. Why? Because solids have the least amount of entropy, everything's much more organized. But in case of gas, molecules have a lot more randomness, much more disorderness, meaning they are going to be at higher entropy. So it's based on the idea of solid have the least entropy, liquids have more entropy, gases on the other hand have even more entropy or the highest entropy out of all these three states. Okay, so if I ask you to predict what is the sign of entropy in this case, you can say entropy, change in entropy in this case, change in entropy will have a positive sign, or entropy of the system is going to be greater than 0, right? So now this is, I already explained to you, but let's say if we are talking about a particular reaction where everything is gas, okay? We'll pick an example. So let's say I give you a particular reaction of hydrogen gas, okay? React with C2H4, which is also a gas, to produce C2H6, okay? This is also a gas. So if I ask you in this case, can you predict or can you tell me, is the entropy of the system increasing or decreasing? How would you tell me that? Okay, so remember we talked about the number of particles can lead to increase or decrease in entropy. So higher the number of particles, higher would be the entropy, right? Now in case of chemistry, if you guys remember, it's easier, instead of counting the number of particles, what is the currency that we usually work with? Oh, my bad. We work with number of moles, right? So in this case, in a reaction like this, we will see which, are we increasing the number of moles by doing this reaction, or are we decreasing the number of moles? So for instance, how many moles of reactants do I have? I have 2 moles of gases right here, right? So number of moles of my reactants in this case is 2, 1 mole of hydrogen, 1 mole of C2H4. How many moles of gas am I producing at the end? Just 1 mole of C2H6, right? So I'm essentially going from 2 moles of gases to 1 mole of gas. So what am I doing to the total number of particles in this system? I'm decreasing the number of particles in the system. So if we are decreasing the number of particles, what would happen to entropy? Entropy is also going to decrease. So now if you're given a chemical reaction like this, how can you predict if a reaction is going to be increasing the entropy of the system, or if delta S is going to be higher than 0, or if delta is going to be lower than 0? You basically look at the change in the number of moles of the particles. So you calculate the number of moles of molecules, change in the number of moles of molecules, which is n products minus n of reactants. If this change in n is a positive number, that means entropy is increasing. If this n is a negative number, that means entropy is decreasing, right? Okay, so let's try to do a couple questions to understand if we can predict what is happening to entropy in this process or not. So let's try question number 1, which represents an increase in entropy. In this case, we have four different options. Water vapor condensing into a liquid, which means what is happening here, water, which is a gas, is changing into liquid. We know that gases have much higher entropy than liquid, which means here entropy is actually decreasing. So that's not our answer. Carbon dioxide gas, carbon dioxide is subliming. Now, what is the definition of sublimation? If you guys remember, sublimation is when something directly goes to vapor from solid. So solid is getting converted into gas. This solids have lost lesser entropy, Gases have a lot more entropy, so this could be one of our answers that we're looking for. Next is liquefying helium gas. So again, liquefying means gas is getting converted into liquid. That's not correct. Proteins forming from amino acids. So if you guys are not familiar with what proteins are, what amino acids are essentially building blocks for proteins. So a lot of amino acids, they combine together to form something that is protein. So let's say these are the amino acids and this is what the protein looks like. So amino acids are going to be arranged one after the other. Okay, so in this case, amino acids are very disordered, but in case of proteins, they are arranged in a particular order, which means this, what is happening to the order in this case, they're getting more ordered, meaning the entropy is decreasing. So this is also not our option, which means which one is the correct answer? P, carbon subliming. Okay, next, the second part. Which of the following processes have a decrease in entropy? Water is freezing. Freezing process essentially means liquid is getting converted into solid. So liquids have more entropy, solids have less entropy. So yes, entropy in this case is decreasing. So this could be one of our options. Isopropanol condenses. Um, Isopropanol is just for you. If you don't know what isopropanol is, just we don't care. What we care about is condenses, right? It's one of the chemicals, but it's condensation that's happening right here. What is condensation? Condensation is gas changing to liquid, right? So gases have more entropy, liquids have lesser entropy. So what is happening to entropy? Again, this entropy is also decreasing. So this could also be one of our options. Next is methanol gas is cooling down. So again, gas is cooling down, meaning it was at a higher temperature before. Temperature was high and now temperature is going down. So higher the temperature, higher is the disorderness. Lower the temperature, lower is the disorderness, meaning entropy again is decreasing in this case. So yes, this could also be one of our answers. Carbon dioxide is going from from gas to solid. So gas here is getting converted into solid. Again, gas to solid, gases have more entropy, solids have less entropy, meaning in this case also entropy is going higher. Oh, sorry, decreasing. In this case also entropy is decreasing. So all our cases, entropy is decreasing. All the above processes have a decrease in entropy, which is correct, meaning our answer is E. Okay, easy. So let's move on to the next concept. Oh, okay, which is right here. Can you predict the sign of delta S for these reactions? Okay, so in the first reaction, what do we have? We have calcium carbonate, which is a solid, reacts with proton, which is aqueous, is changing to calcium ion, water, which is liquid, and carbon dioxide, which is gas. So this is a very heterogeneous phase of reaction. So we have different phases in one reaction. Now, what do you remember? We have something solid, we have something aqueous, we have something liquid, we have something gas. So which phase has the highest entropy? Gases have the highest entropy, meaning in this case, these, even though they are present, gas in this case would have the highest entropy. So whenever you have a reaction with mixed phases, you only look for the moles of gases. So in this case, if I want to figure out what is the delta N, so how many moles of gases do I have? Delta N again is N of products minus N of reactants, right? So how many N of products do I have? N is number of moles of gas. How many moles of gas here? We only have 1 mole of gas, so that is going to be 1 mole. And how many moles of gases in the reactant side? It is 0. So it's going to be 1 minus 0 gives us 1 mole. So our delta N is positive, meaning our delta S is also going to be positive. So delta S is increasing. Predict the sign of delta S. If delta S is increasing, sign is going to be positive. So it's going to be greater than 0, meaning sign S, delta S would be have a positive sign. Easy. Let's look at second example. So if I have a reaction, can you predict the sign of delta S? So it's gas. producing gas, and another mole of gas. So easy question. We want to figure out what is delta N. What is the N of reactants here? 2. N of products, 4 plus 1, which is 5. So delta N is going to be 5 minus 2, product minus reactant, which is 3. So since it's a positive number, our delta S is also going to have a positive sign. Okay. Moving on to the last part, which is OH minus aqueous, NH plus aqueous is changing to water, liquid. Okay. So now in this case also we are going to use the concept, even though we don't have any gases here, but we will be talking about how can we figure out, we are going to use the same idea here to figure out if our in this case of our reaction, if delta S is going to be positive or negative. So number of moles of our reactants is, total mole is 2 moles. Even though we don't have gas, everything is kind of liquid in this case. This is liquid water, this is aqueous, meaning it's in water, right? How many moles of product do we have? 1 mole. So what is delta N in this case? It's 1 product minus reactant, which means -1. So since my delta N has a negative symbol, which means I'm reducing the number of particles, my symbol for delta S is also going to be negative. Okay, it would be decreasing the entropy of the system if this reaction goes in forward direction. Okay, there are a couple more examples for you guys. You can practice those on your own, right? Should be fairly simple. So you can pause the video, practice these questions on your own. Answers are given to you in the slide, PowerPoint slide on Canvas. So one thing that I forgot to mention, if for some reason your delta N comes out to be 0 for a particular reaction, that means you cannot predict the sign of delta S. So your answer would simply be, we cannot predict what is the sign of delta S in this particular reaction. Okay. All right. I'm going to move forward. And now we'll talk actually numbers. So up until now, what we were discussing was the sign of delta S. So is it increasing or is it decreasing? Now, if I ask you to calculate the actual numbers, how can we do that? Entropy of 1 mole. How can we calculate entropy of 1 mole of a substance at room temperature, which is 25 degrees Celsius, and 1 atmospheric pressure? Change in the entropy of a reaction is given by entropy of the products minus entropy of the reactants. So sum of all the entropy of the product and minus sum of entropy of the reactants. And what is this S naught that you're seeing right here? S naught stands for standard entropy, which is very similar to what you guys might have seen in delta H naught. This is standard enthalpy. In this case, we are talking about standard entropy. Standard entropy is defined as entropy of 1 mole of a substance at 298 Kelvin, which is room temperature, and at 1 atmospheric pressure. So if we are asked to figure out what is the delta S naught for this reaction, so what is the entropy change for this particular reaction, you take sum of the entropy of the products and take the difference with sum of the entropy of the reactants. So it would be, this has the very similar concept as delta H. If the reaction is AA plus BB gives CC plus DD, these small a, B, C, and D are the stoichiometric coefficients, and capital A, B, C, and D are our reactants and products. Okay, so delta S of the reaction in this case would be C, which is the stoichiometric coefficient, times the standard entropy of C, plus D, small d, which is the stoichiometric coefficient of our product D, times the standard entropy of D. So we add the entropy of the products, which is the sum, minus, then you add up the entropy of the reactant, similar manner, A, small a times the entropy of A, small b plus small b times the entropy of B. So this is essentially the formula for calculating delta S for a particular reaction. Okay, so what kind of question you can expect? A reaction will be given to you. and delta S naught values for the reactants. Each reactant and each product will be given to you. You will be using those values to calculate delta S naught for the reaction using this particular formula right here. Okay, let's take a look at a couple examples. So this is fairly simple. For instance, question number 1. Calculate the delta S naught for the following reaction of carbon dioxide solid is changing to carbon dioxide gas. S naught in joules per mole Kelvin is given to you for carbon dioxide. It's 187.6. And for CO2 gas is given to us as 213.7 joules per mole Kelvin. So what is delta S naught for this particular reaction? First thing we have to do, whenever a question is given to you like this, make sure that the reaction is balanced. That's the most important thing here. Okay, if you don't balance the reaction, your answer is not going to be correct. So in this case, the reaction is balanced. So what would be delta S naught? Is going to be S of, okay, second, S naught for the products minus S naught for reactants. So in this case, product is, I only have one of these, so it's going to be 1 times 213.7 joules per mole Kelvin minus 187.6. Again, we only have 1 mole of that, joules per mole Kelvin. That's it. We take a difference of that, and that would give you your delta S naught for 26.1 joules per mole Kelvin. Easy. So now you can see from here, as we have predicted, this solid is changing to gas. We can predict that delta S for this reaction should be a positive value, right? And so is true with your final answer as well. Okay. Let's look at the second question. Calculate delta S naught for the following reaction. Calcium carbonate changes to CO2 and calcium oxide. Entropy, standard entropy for each of the reactant and product is given to us. So first thing, important thing here is make sure the reaction is balanced. 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygen, total of 2 plus 1, 3 oxygen on the product side as well. So delta S naught in this case is going to be sum of S naught for the products, right? So we have 2 products here. So first thing we are going to do is we are going to add these. I only have 1 of carbon dioxide, so it's going to be 1 times 213.7 joules per mole Kelvin plus the second product, which is calcium oxide, which is 40 joules per mole Kelvin. We take sum of our products minus sum of our reactant, which is 1 mole, so 1 times 92.9 joules per mole Kelvin. So it's product minus reactant, which would give you your final answer as 161 joules per mole Kelvin. Okay, so you can also confirm if your answer kind of like sign is correct or not. Calcium carbonate is solid, gas, and solid. So this has, if there is a gas component, we only go by the gas component. Okay, so how many moles of gas is 0? How many moles of gas is here? 1, which means delta N is going to be product minus reactant. So 1 minus 0 gives you 1. So we can predict from here delta N is positive. So delta S is positive, which means that yes, our answer is probably correct. Okay, again, you don't have to do this part. I just did this as a confirmation. You don't, this part is not needed. Okay, the last part. What is needed is just right here. 161 joule per mole Kelvin. Okay, moving on. You can pause the video right here and try to solve for this question. Okay, and I will solve with you guys. Okay, so just pause the video, do it yourself, and then you can come back and look for the final answer. Okay. Okay, so I'll work on the answer for now. So we have Al2O3 plus 3H2 changes to 2Al plus 3H12. So this is a chemical reaction. Delta S naught, sorry, S naught for each of the reactant and products is given to us. Question is calculate delta S naught for reduction of aluminum oxide by hydrogen gas. So first thing, we identify if a reaction is balanced or not. How many aluminum in the reactant? 2. Product 2. Oxygen is 3. Oxygen is 3 in the product. Hydrogen is 6 in the reactant. Hydrogen is 6 in the product. So our reaction is balanced. So now what would be delta S naught for this particular reaction? Delta S naught is going to be sum of products. So this right here, what I drew is the symbol for sum, right? So we are going to essentially add up. Let's just ignore this. Okay, don't want to confuse you guys. So it's going to be sum of products. How many products do I have? 2. So we'll go one by one. Aluminum. How many moles of aluminum? We have 2 moles of aluminum. So it's going to be 2 times the entropy of aluminum. Plus, how many moles of the second product? 3. So 3 times the entropy of water. That is sum of our products minus, we are going to do sum of our reactants, which would be how many reactants? 1 mole of Al2O3. So it's going to be 1 times entropy of Al2O3 plus the second reactant, which is hydrogen, which is 3 times the entropy. So these are S naught values, S naught of hydrogen gas. Okay, so now let's just plug in the values. 2 times aluminum is 28.3 plus, so when you have to plug this into the calculator, that's where most of the people make mistakes. Okay, so make sure you plug in with the calculator like this, having multiple parentheses, plus 3 times entropy of water, which is 188.7 minus S of Al2O3, which is 51.00 plus another parentheses 3 times S of hydrogen gas, which is 130.6. Okay, so if we solve for this, this will give you your final answer as 179.9 joules per Kelvin per mole. Okay, so that would be our final answer for delta S for this particular reaction. Okay, now the important thing here is what can I change in a question like this? So in a question like this, I could give you different units for different S naught. So just make sure your units are always constant. So joules per mole per Kelvin, everything is in joules per mole per Kelvin. If one of these values I gave you as kilojoules per mole Kelvin, then make sure you convert that into joules per mole per Kelvin or otherwise, okay, vice versa. So all of these should be in the same unit, otherwise your answer is not going to be correct. Okay, so your final answer is delta S naught 179.9 joule per Kelvin. Okay, so let's move on to the next. So based off of now, we learned how we can predict the sign of delta S, but we still don't know how we can predict if a reaction is spontaneous or not. Okay, now to do that, we come to another concept, which is the second law of thermodynamics. And this law states that entropy of the universe increases in a spontaneous process. So meaning the delta S for a universe will always be greater than 0 if the process is spontaneous. And it would remain unchanged in an equilibrium process. So if for a process that is in equilibrium, delta S for the universe is going to be equal to 0. So these are the two things that this law helps us predict. So we have to figure out, if we want to predict if a reaction is spontaneous or not, we have to look at what is the sign for delta S universe. What is delta S universe? Delta S universe is change in the entropy of the system plus the change in the entropy of the surroundings. So by after adding these two, our value should be greater than 0. That's when we can say that our reaction is spontaneous, which is quite difficult to do because uh, if a chemical reaction is happening, usually we can only talk about or measure what is the difference in the entropy of the system, right? Which we just saw, how to calculate difference in entropy of the system. But it's very difficult to calculate the entropy of the surroundings. So we'll talk about how we can use this information right here, what you just saw, that the entropy of the universe has to be greater than 0 to figure out a way to predict spontaneity of a reaction. Okay, but before that, we'll talk about third law of thermodynamics, which is also fairly simple. Third law of thermodynamics states that at absolute temperature, which is called the 0 Kelvin temperature, is the absolute zero temperature, the entropy of a perfectly ordered pure crystalline substance is 0. So entropy of a substance at temperature 0 Kelvin is always going to be 0. You can pick any substance. This temperature 0 Kelvin is the lowest temperature that's possible, meaning that at this particular temperature, any substance is going to be perfectly ordered. So the best order that is possible is going to be possible at this temperature, which means that there is not going to be any disorderness. So the value of microstate, which is W, is going to be 0, meaning our entropy is going to be 0. Okay, that's the third law of thermodynamics. Now, what I just told you, that in order to predict, we still don't know how we can predict if a reaction is spontaneous or not. We will be, in order to predict if a reaction is spontaneous or not, there was another term that was introduced, which is called Gibbs free energy. This is sometimes also referred to as Gibbs energy or free energy or Gibbs free energy. What is this? This is the maximum energy in a reaction that is free or is available to do useful work. Okay, this term right here can help us predict if a reaction is spontaneous or not. How? It is related to enthalpy and entropy in this way. So G equals H minus T delta S. G is the free energy, H is the enthalpy, T is the temperature of the system, and S is the entropy of the system. So whenever you see anything written like this, and if the system is not listed, that just means we are talking about system. So most of the time, since we are usually focused on a system, we do not write system everywhere. Okay, so this part, if nothing is written, you can just assume we are talking about a system. So free energy of a system equals H of a system minus enthalpy of a system minus temperature of the system times entropy of the system. Okay, now this term, let me go to the next slide, and I will help you understand how this term helps us predict if a reaction is spontaneous or not. Okay. Okay. So to confirm, I just showed you previously that delta S of universe equals delta S of the system plus delta S of surroundings. Correct? We saw that at equilibrium, delta S of universe equals 0, which means that delta S of the surroundings will be equal to negative delta S of the system, correct? So in this expression right here, what I did, I replaced delta S of surrounding with this. Delta S of universe will be equal to delta S of system minus delta S of plus delta S of surrounding. So plus, I replace delta S surrounding by this right here, which is negative delta S of system, right? Another thing that I kind of skipped in this slide is that delta S of the system can be given by delta H of the system divided by temperature, and this is true at equilibrium. Okay, I'll explain later on how we got this, but for now, remember delta S of the system equals delta H of the system over temperature. So now I can replace this equation right here, which would give me delta S of universe equals delta S of the system minus T delta H of the system divided by T. Now if I multiply both the sides by temperature, that would give me this right here, correct? So now if I multiply both the sides by -1, this I multiplied both the sides by temperature, and that gave me this. I multiply both the sides by -1, and that would give me this right here. So what I just showed you is G is, in the previous slide, G is H minus T delta T times S, which means change in G would be equal to change in H minus change in S times T, right? I can write the same expression in this form, and that's exactly what you see right here. So change in H minus T change in S of the system. So this right here I can replace with delta G, correct? So this term right here is called the free energy. So delta G is free energy, which is equal to minus T delta S of the universe. So this can help us predict, the sign of delta G can help us predict if the reaction is spontaneous or not. Why? Because we know from second law of thermodynamics that delta S of the universe will always be a positive number, or it is going to always increase when a reaction is spontaneous. So if a reaction is spontaneous, delta S is going to be a positive number, meaning this is positive. We know that temperature in Kelvin is always a positive number. Okay, as I showed you, the lowest temperature that is possible is 0 Kelvin. So the temperature is a positive number. Delta S of the universe for a spontaneous process is a positive number, meaning the whole term right here is going to be a negative number. Why? Because there's a negative sign right here, meaning delta G is going to be a negative number for a spontaneous process. So essentially, whenever there is a spontaneous process, delta G for that process is going to be a negative number, and that is the only thing that can help us predict if a reaction is going to be spontaneous or not. So remember, for a spontaneous reaction, this is the most important thing to take away from all this slide. I do not expect you guys to know this derivation. I will never ask you to derive it. I will never ask you to memorize any of these terms right here. Okay, all the equations that you see I will be providing to you. You will never need these equations. What I did here, all I showed you was I wanted to come back to this. Okay, so only takeaway message from this slide is that change in energy, change in free energy of a system has to have a negative sign for a reaction to be spontaneous. That's the only thing you should remember. If I ask you, can you tell me if this reaction is spontaneous or not? Only way you can tell me yes or no is by looking at the sign of delta G. If delta G has a negative sign, the reaction is spontaneous. If delta G has a positive sign, the reaction is non-spontaneous. Right? That is the only important thing to take away from here, and that's the most important thing that you should remember. Let me go to the next slide, please. So now you know, for a constant temperature and at constant pressure, delta G equals delta H minus T delta S. Again, all these equations I will be given to you in exam. I don't expect you to memorize it. But only thing I want you to memorize here is that if delta G has a negative number, if it's a negative number, that means reaction is spontaneous. If delta G has a positive number, or it's a positive sign, that means reaction is non-spontaneous. Okay, and if delta G is equal to 0, the reaction is at equilibrium. So what you see right here, delta G is less than 0, meaning it's a negative number. Reaction is spontaneous in the forward direction. So whatever direction is given to you, that reaction is spontaneous. If delta G for reaction is greater than 0, meaning it has a positive value, it's a positive number, the reaction is non-spontaneous as it is written. So if I write A is changing to B, and I tell you delta G for this reaction is positive, this reaction is non-spontaneous, but the reverse of this reaction is now going to be spontaneous. Since we know either a reaction can have only two ways, either it is spontaneous or it's non-spontaneous, right? So if this is non-spontaneous, the reverse of this is going to be spontaneous. All right. Okay, so that's the only thing that I want you guys to remember. Next thing, how will this help us predict if a reaction is spontaneous or not? You can also predict, now you can use this equation to predict the sign of delta G. If you know what is the sign of delta H, if you know what is the sign of delta S, you can predict what is the sign of delta G. And you can predict if a reaction is going to be spontaneous or not. And you can predict how you can make this reaction spontaneous by changing the temperature. So only variable in this reaction is temperature. We can change temperature, okay? But remember, temperature here is in Kelvin, and only value that's possible for temperature is positive. Negative value of temperature doesn't exist. Okay, so you can assume in any case, temperature is always going to be positive. So now let's see a couple examples how we can predict. So for instance, if my delta H has a positive value and delta S also has a positive value, can I predict if this reaction is going to be spontaneous or not? Let's pick another example to begin with. Let's say if I have this second example, delta H is positive and delta S is negative. So if delta H is positive, my this value is always going to be positive, right? Minus T is always a positive number, right? So you can ignore T right here, times delta S, which is a negative number. So this value is going to be a negative value, okay? So you can assume this is plus value, whatever value is, plus X, I don't care, minus T is whatever, we don't care. Delta S has a negative value, negative Y. Okay, what would this final value come out to be? Plus X minus minus will become positive, so that means plus X plus Y, which means this value is always going to end up being positive. You can have any value of X, you can have any value of Y, right? Temperature, any temperature, right? It means delta G is always going to be a positive number. So if delta G is always positive, means reaction is always going to be non-spontaneous. It will be spontaneous in reverse direction, but in this particular direction that you're interested in, the reaction is always going to be non-spontaneous, right? Okay, let's predict if we can do this for the second time with different symbols. So here what you're essentially doing, just looking with the symbols, working with symbols. Okay, so let's pick this third scenario where my delta H is a negative number, delta S is a positive number. So if my delta H is negative, so this is going to be equal, delta G will be equal negative H, right? So let's say it's a value of X, I don't care what the X is, minus times temperature, again, it's going to be a positive value, so you can ignore it, times delta S. Delta S is a positive number, so it's going to be plus something plus Y. I don't know what Y is, right? So eventually I can write this expression as, let me write it here. It's easier. X equal, this would be equal to negative X, negative Y, right? Negative plus minus and plus will become negative, which means I can have any value of X and I can have any value of Y. Negative and negative will always give me a final value of negative. Is that correct? Which means in this scenario, in that scenario number 3, delta G is always going to be a negative number. So if it's always negative number, reaction will always be going spontaneously at all temperature. You can have a low temperature, you can have high temperature. Reaction will always be spontaneous because this is always going to give us a negative value of delta G. Okay. Okay, now let's pick another. Now let's talk about the other scenarios. So for instance, let's go back to our first scenario. What would happen in the first case? So if my delta H is a positive value, delta S is also a positive value. How can I, oh my bad, let me change this to pen first. Okay, so if both of these are positive values, what would happen? Delta G is going to be equal to, delta H is positive, so it's plus X minus, temperature is always positive, so we can ignore it. Delta S is also a positive value, so plus Y, correct? That would give me it equal to X, which is a positive number, minus plus minus is going to create a minus Y. Now what do I know here? So my first term is X. I cannot change that value, right? This is for a particular reaction. This is dependent on reactants and products. Which variable? If I want this reaction to be spontaneous, I want my value of Y to be a greater value. Is that correct? I want delta G to be completely negative value, meaning I want Y to be a greater value. Now delta S is also a fixed number. I cannot change it. What can I change? My variable here is temperature. If I increase the temperature, my value of Y will increase, correct? Which means my final answer is going to be a negative value. So if this reaction is happening at a very high temperature, it is going to be spontaneous. But at low temperature, this reaction is going to be non-spontaneous. Okay. Similarly, we can predict the fourth scenario. Let's work with the fourth scenario. What is happening in case of 4? Delta H is negative, which means I can write this as equals delta H is negative. Let me just write here. Delta H is negative, so minus X, whatever is the value of X, minus temperature is something, I don't know what's the value. Delta S is also negative, so it's going to be a negative Y value, correct? Equals negative X, negative and negative will become positive, plus Y. Again, we come back to a scenario where if my value of delta H is higher, I'm good. But if my value of Y is higher, then that means that delta G is going to be a positive number. So it comes back to, again, we cannot change the value of delta H, we cannot change the value of delta S. Only variable here is temperature. So if I want a reaction to be spontaneous, in this case, I want my temperature to be low so that my value of Y is low. So this reaction will be spontaneous at low temperatures, but at high temperatures, this reaction will be definitely non-spontaneous, because at high temperature, my value of Y will be higher. If Y is higher, my value of delta G is going to be a positive value. Okay, so this helps you kind of predict if a reaction is going to be spontaneous or not, and if a reaction, by changing the temperature, can you make a reaction spontaneous or not, if we know the values of delta H and value of delta S. Okay, so how will we use these values? Let's see. Okay, so let's try one question. For the reaction 2NO plus O2 changes to 2NO2, delta H naught is given to us, delta S naught is given to us. Which statement is true? The reaction is spontaneous at all temperatures. The reaction is only spontaneous at low temperature. Reaction is only spontaneous at high temperature. Reaction is at equilibrium at 25 degrees Celsius under standard conditions. So we'll come back to part B separately, because we'll have to calculate this, if the reaction is at equilibrium or not. Because for equilibrium, remember, we have to figure out that delta G, at equilibrium, delta G is going to be 0, right? So we cannot predict that. We'll have to calculate that. So we'll come back to part D later on. But maybe let's try the other parts, and maybe we have our answer just by predicting the sign of delta G. Okay, so now we know that delta G is delta H minus T delta S, right? So we are going to use this, and what we just saw about different scenarios, we are going to use that idea to figure out if our reaction is spontaneous or not. For spontaneous reaction, we want delta G to have a negative value. Okay, so what is the symbol of H? H here is a negative sign, so assuming it's negative X, minus temperature, again, has to be a positive value. Delta S is also negative, so it is negative Y, which means this is negative X, negative negative makes it positive, plus Y. So now again, I'm in a scenario where my spontaneity of reaction depends on which variable? Temperature. Because delta H is constant, I can't change it. Delta S is constant value, I can't change it. Only thing I can change here is temperature. So in order to have my delta G to be negative, I want my value of Y to be small, meaning I want this value to be small. So meaning I want my temperature to be low, correct? So this reaction is only spontaneous at low temperature. So my answer is B. Okay. The second kind of question is right here. The question says, at what temperature in Kelvin will a reaction become non-spontaneous? When delta H is given to us and delta S is given to us. So in this case, the question is asking us for temperature. Now we know that delta G, for a reaction to be spontaneous, delta G has to be a negative value, correct? We cannot solve a question like this. We also know, let me just come to this part first. So we know delta G is delta H minus T delta S. If I want to figure out what is temperature, I need a value of delta H, which is given to me. I need value of delta S, which is given to me. I need value of delta G, which is not given to me in question. But the question tells me that the reaction would become non-spontaneous. What do I know? In questions like this, you will solve assuming that delta G is equal to 0. Why? Because for a reaction to be non-spontaneous, delta G has to be greater than 0. For a reaction to be spontaneous, delta G has to be less than 0. So what is the actual number that controls spontaneity and non-spontaneity here? 0. Anything greater or lower, correct? So we are going to basically assume that we are solving for delta G value of 0. Okay, so if delta G is 0, delta H is minus 50. We cannot assume our number to be anything else, right? We cannot assume it's a positive or negative number. We can't just give it a value. Only value we can give it is 0. So at 0, a reaction would be equilibrium at this particular temperature. So we'll calculate what is the temperature when reaction is at equilibrium. And based on that, if the temperature goes any lower than that or any higher than that, our reaction is going to be either non-spontaneous or spontaneous. So that's the actual value that we can predict. Equals, sorry, minus temperature times delta S, which is given to us, minus T times 20.50 joules per Kelvin per mole. So make sure you're looking for units. Okay, what is wrong in this expression right here? I have delta H in kilojoules and delta S in joules. So if I want to calculate the answer for this, I need both of them in kilojoules or both of them in joules. So I can write this as minus 50.20 kilojoules per mole minus, and I'll convert this into kilojoules. That would give me T times 0.02050 kilojoules per Kelvin per mole. Correct? I can do that. And now if I solve for temperature, you will get a value. How will you solve for temperature? You will add both the sides with 50.20, correct? And then you will take this temperature and multiply it, divide that number by both the sides by 0.02050, and that would give you a temperature as 24, let me see, what is the answer that I have? 2448 Kelvin. So our answer is going to be C. Actually, your answer is solved much prettier right here. So you can use this solution to get to this particular temperature. So this temperature is where the reaction is at equilibrium. So if I change the temperature anywhere from here, my reaction would be either spontaneous or non-spontaneous. Okay. Okay, moving on. Next thing we are going to talk about is the standard free energy of formation. So just how we have talked about standard, which is energy, standard entropy, standard enthalpy, we also have standard free energy. Okay, what is standard free energy of formation, which is depicted as delta GF? Okay, naught is the free energy change that occurs when 1 mole of a compound is formed from its element in their standard state. So whenever a compound is formed, 1 mole of the compound is formed, whatever change in free energy happens, that is called as standard free energy of formation. It's given by delta G naught. Naught is here, whenever it's standard, you put a naught. F is formation. So this is for a compound, right? Remember, elements are never formed. Elements exist in nature. For instance, if I talk about freely existing elements like nitrogen gas, oxygen gas, these just exist. These do not form. So whenever you talk about delta G naught F of any element, it is always going to be 0 because there is no formation involved here. These just exist like this. Oxygen just exists like O2. Hydrogen just exists like H2. Okay. So whenever you see an element, iron, it just exists like Fe. So delta G naught F for iron is going to be always 0. okay, because it just exists like it. There's no energy change that happens in this. There's no reaction for formation of iron. Okay. Next thing is, what is delta G naught for a reaction? That is standard free energy of a reaction. Again, it's the same concept. You are going to do sum of the energy of the products minus sum of the energy of reactants. Okay, that is the free energy change for a reaction when it occurs under standard conditions, meaning at 1 atmosphere at 25 degrees Celsius. So if I have a reaction of AA plus BB gives CC plus DD, how would I figure out what is delta G naught for the reaction? It is going to be sum of all the reactants, sum of all the products, which means C times delta G naught for C. C would be the stoichiometric coefficient plus small d times delta G naught for our product D, add them up, minus addition of small a times delta G naught formation of A plus B times delta G naught formation of B. So it's the same concept, like this is the same idea for enthalpy, entropy, and G. Okay, how can I ask you a question? I'll give you entropy values for A, B, C, D. I'll give you enthalpy values for A, B, C, D and ask you to calculate delta G naught. So you figure out what is delta H for the reaction, you figure out what is delta S for the reaction, and then you can plug those values into the expression delta G equals delta H minus T delta S, figure out what is delta G. Other way I can ask you a question is, I'll give you delta G naught F values for all the reactant and product, and then I ask you how much is the delta G naught for a reaction. You just plug in those values like this and calculate delta G naught. So those are the two ways you can figure out what is delta G naught for a reaction. Okay, so here's one question for you guys. So we have calcium carbonate changing to calcium oxide plus CO2. The question gives you what is delta H naught, what is delta S naught, and then it gives you this expression. It tells you at 25 degrees Celsius, this is the value of delta G naught. At what temperature will delta G naught be a negative value? Or at what temperature will the reaction become spontaneous? Again, this information that's given to you is just extra information to confuse you. Okay, the question is, at what temperature will delta G naught be negative, or will the reaction be spontaneous? So you guys remember this expression right here. If we want to figure out the temperature when delta G naught is negative or the reaction is spontaneous, the only way we can figure that out is assuming delta G naught is 0. So again, we are going to do the same idea. Let me fix that. Okay, so we are going to use the same concept. We know, sorry, let me pull that back up. We are going to solve for temperature when delta G naught is 0. So we'll rewrite this expression. We'll assume delta G is 0. We have the value of delta H, plug in the value of delta H, plug in the value of delta S, plug in delta G as 0 and solve for temperature. And if you solve for that, same approach, temperature will come out to be 1108 Kelvin. So essentially, any temperature above 1108 means the reaction will be spontaneous. So here's one question, kind of question you can expect for delta G. Calculate delta G naught for reduction of aluminum hydroxide by hydrogen gas. So again, the equation is given to us, where aluminum oxide reacts with hydrogen gas to produce aluminum in water. What's given to us in question is delta G naught F for all of these. Aluminum is 0, Al2O3, hydrogen gas, H2O. Now in this question, aluminum delta G naught F is given to you as 0 and hydrogen gas is given to you as 0. But ideally, it's possible that these two values will not be given to you in question. So you should be able to predict if these values are missing, why are they missing? You should be able to figure out that delta G naught F or formation for hydrogen is always going to be 0. Why? Because this is an element. Same thing for aluminum. Since it's an element, it's always going to be 0. So in case these values are not given to you in question, you would still be able to predict that these values are actually 0. How can we figure this out? Based on the same concept, delta G naught of a reaction, G naught for a reaction is going to be delta G naught of products minus reactant. So we'll do sum of products. Products, how many do I have? 3 of water. So 3 times G naught F of water plus 2 times of aluminum. Remember the stoichiometric coefficient, 2 times G naught F for aluminum minus reactants. So sum of the reactants is going to be, first reactant is Al2O3, which is only one reactant, so it's going to be equal to G naught F for Al2O3 plus G naught F for hydrogen. In this case we have 3 moles of it, so it's going to be 3 times G naught F for hydrogen gas, which in this case this and this value is 0, so it makes it easier. So it's going to be 3 times, don't forget the signs that are given to you, 3 times water, which is 3 times negative 228.6. This is 0, so I can ignore it. Minus Al2O3 is given to me as negative 1576.4. Again, one thing I forgot to put here is the units. So make sure you put the units. It's going to be 3 moles of this times unit of G is given to us as kilojoules per mole. Same thing here. This is 1 mole. So this is kilojoule per mole of this times 1 mole of this plus hydrogen is 0, so we can ignore it. Mole and mole got cancelled, mole and mole got cancelled. When you solve for this, you'll get your final answer in kilojoules. So if you solve for it, it should give you 890.6 kilojoules. So it's the same idea, 2 times of this, which is 0, so everything is 0. 3 moles of this, mole and mole got cancelled, your answer is in kilojoules. So eventually it comes out to this, and it would give you a delta G naught of 890.6. Okay. The other kind of question you can expect is like this. So I'll let you guys actually solve this question on your own. What happened in this question? It's based on the same concept. Okay, this is just math now. If you understand the concept, this has nothing else, no other extra concept of chemistry. Only thing you have to understand now is the math. Okay, so determine delta G naught F for CH4 for the following reaction. Reaction is given to us. Delta G naught for the reaction is given to us. See, this is the reaction, this is delta G naught given to us for the reaction in kilojoules. What the question is asking, can you figure out what is G naught F for methane? So we have to solve for this. Okay, now based on the same concept, if the delta G naught for reaction is given to us, which means delta G naught for this reaction is going to be equal to product, sum of product minus sum of reactant. What are the products? I have 2 moles of carbon dioxide, so 2 times G naught F of CO2 plus 4 times G naught F of water minus 2 times G naught F of CH4 plus 4 times G naught F for oxygen, which I know should be always 0 since it's an element. So we know what is G naught F. Yes, that is given to us right here. We know what is G naught for CO2. Yes, that's given to us. We know G naught for water, given to us. We know G naught for oxygen. Yes, it's 0, given to us. What we have to solve for it is right here. Okay. So everything's given to us except one value. Only thing now is you just have to do the math to solve for this particular value right here. So I'm going to leave you with this question and you can solve for the final answer. Okay. The last type of question that you can expect, I already gave you an example of this kind of question. So question is calculate G naught for the reaction. Again, it's a reduction of aluminum oxide by hydrogen gas at 25 degrees Celsius, which is room temperature, so equal 298 Kelvin. Delta S naught is given to us, and delta H naught F for each of these reactants and product is given to us. The question is, can you figure out what is delta G naught? What's given to us is delta S naught, right? What is the only equation that you guys know for delta G? If I want to figure out delta G for a reaction, it would be delta H naught minus T delta S naught, correct? Do I have the value of S naught? Yes. Do I have temperature? Yes, it's 25 degrees Celsius, which is 298 Kelvin. Correct. I have the temperature. Do I have delta H naught for the reaction? Remember, all of this is reaction. RXN, RXN, RXN. Okay. Do I have delta H naught? I don't. But what do I have? I have delta H naught F for all of these. So first thing, I'll have to solve for this. Once I can solve for this, I will have all the values to calculate what is delta G naught. How can you solve for delta H naught? Same idea. Delta H naught for a reaction is sum of the product, delta H naught F for products, minus sum of the reactants enthalpy. Okay, so we are going to use that concept right here. Ignore the bottom portion for now. It is delta H naught F products sum. This I told you is sum minus products. So based on our reaction, we have 2 moles of aluminum. So it's going to be product aluminum 2 times delta H naught of F plus 3 moles of water. So 3 times H naught F of water. Sum that up minus reactants, which is 1 mole of Al2O3, so 1 times delta H naught F for Al2O3 plus 3 moles of hydrogen, so 3 times delta H naught F of hydrogen. Again, the same concept still lies. Whatever exists in their elemental form, there's no delta H naught F for it. Why? Because they're not being formed, they just exist. So this value and this value is going to be 0. If you plug in your values, as the question tells you to, you will be able to calculate delta H naught for the reaction as 944.4 kilojoules. Now, if you plug in this value into this expression right here, we have delta H naught now. Temperature is given to us, delta S naught is given to us. Only thing remember here, the catch again is our H naught comes out to be in kilojoules, but our S is given to us in joules. So you make sure you convert, you should have both these values in the same unit. Okay, so we converted this into kilojoules, and that would give us our delta G naught as 890.8 kilojoules. Okay, that is the end of this part of the topic. I'm going to end this video right here, and we'll continue with how delta G can be related to equilibrium. So remember, I told you equilibrium, once it starts, is going to go till the end of this whole course. So there is going to be equilibrium coming in shortly, and we'll talk about that in the next video.